Things on inclines. That's what we're looking at today. Let me frame you guys on what exactly we're examining by showing you my lovely frictionless cart and track. And here's my cart. And what I want to try and figure out as I push this thing up is if I know the velocity that I push the cart with, can I figure out exactly how high this is going to go? Now you should be saying, yes, we can already do this because we could draw a free body diagram, we could figure out the acceleration, and using fancy kinematics, we could probably figure out exactly how high up the ramp it goes. But there's an easier way of doing this, and that's with energy. So that's what I want to walk you guys through in this video. Let me adjust this. There we go. Things on inclines. So if I give this cart a push up the ramp, how far will it travel? I'm just going to call this angle theta, and it could be any given angle in a problem that you'd see. Also, this is a low friction track, so I'm not going to examine friction at all on this cart. And what I want to know is, could I figure out this distance that the cart travels given this theta? So I'll start with my lull diagram, and at the very beginning, I give it a push, so every bit of energy is in kinetic. There's no spring, and this is meant to be UG. There's no gravitational energy because I'm calling this point my zero line. The system is the cart tracking Earth. Remember, you need to use the Earth in the system in order for there to be any energy from potential energy, because the Earth is pulling down this cart. So that's our system. And at the very end over here, all of my energy has converted into gravitational energy. So all 5 of my boxes are now over here. At the very top, for a brief moment, there's no more kinetic energy. There's still no spring, and it's frictionless, so there's no change in internal energy. So we've got a perfect transfer over here. I'm going to write an energy conservation equation. Now there's no work coming into my system, so I could say the initial energy will be the final energy. My initial energy was just kinetic energy. My final is gravitational energy. So I will write an expression to say that these are equal. The kinetic energy initial has to equal the potential energy final. And I know my equations for both of these. The generic equation for kinetic energy is 1/2 mv squared, and the potential energy equation is mgh, or h is the distance from your zero line, and your zero line is right here. So I'd set my initial equal to my final in kinetic and potential and say 1/2 mvi squared is equal to mghf. We need to define what this hf is. It's the height above the zero. This is not the distance traveled, this is the height above the zero line. So that's what we're going to solve for, and with that we could then get distance using some trig. M's cancel out. Notice that mass has no effect on how high this thing will go. And I solve for my h final. So if I know my velocity, I obviously know this g constant is 9.8. I could figure out the height up the ramp that you go. And to figure out the total length, I would use the sine function and relate the sine of theta equal to the height over the distance. Notice that all of this is so much simpler than drawing a free body diagram using Newton's second laws and then using kinematics. So when we have a motion problem, we should be getting in the hang of using this simpler concept of energy, and if energy can't work for us, then we would move over to the free body diagram. So could you use this energy analysis to determine the velocity of the cart at the bottom of the ramp if you drop it, say, 0.5 meters up? So if I put it down on the cart, how fast will it be going when it reaches the bottom? You should be able to do that, sort of this problem in reverse. Hope you found this helpful.